We know that consumer surplus is an area under a graph, so it's bounded by a graph on the top side. It's bounded by this horizontal line on the bottom side. What is the tool that we have in calculus for computing such an area? An integral, exactly. This is the whole kind of second half of calculus is devoted to building out the theory that will allow us to compute a quantity like this one. So this purple area can be thought of as an integral. Okay. My first question is an integral of what? So what is the function here that we're going to be integrating? You can kind of see part of the formula over here. I don't care for the moment what the formula is. It's the formula that...
0 and 50.
Okay, great, right. So the limits on my integral tell me how far to the left and how far to the right I need to integrate, which x values I need to integrate over. And that's going to be, in this example, 0 out to 57. My equilibrium quantity, the quantity that maximizes my profit. So in this example, at least, integral from 0 to 57. And then the question is, what function, what mathematicians call the integrand? What's going to go inside of my integral, and my integral here is being taken with respect to x. So I'm going to put a little dx here at the end. So what is the function that I'm integrating? This kind of has a two-part answer. On the one hand, the consumer surplus region here is bounded on the top by my demand function. So the upper limit of my consumer surplus is going to be just the function, the demand function d of x. So I'm just going to kind of write that in here as d of x for the moment. And because all of your teams started with different project data, you'll have different d of x's that you got from doing the polynomial regression on your test marketing data. So d of x is the upper limit, is one way to think of it. But if I just integrate d of x with respect to x, why am I not going to get the purple area? What am I going to get if I just integrate d of x? I'm going to get the whole area underneath that graph all the way down to the x-axis. Right? So if I just integrate d of x, I'm going to get the consumer surplus added to the total revenue. Right? And maybe that's what I want in a calculation. Maybe it's not. So there's a couple of different ways to go about that. Maybe let's take that observation here for a moment and run with it. That if I just do this integral, I'm going to get purple plus orange. So if I did this and I got some answer, okay, how would I then figure out what the purple area is? If this integral is purple plus orange, how do I get purple back out of it?
You calculate the revenue or the area of the total revenue and then subtract it.
Yes, so exactly. We can do that as a separate calculation and then subtract it out. And that may be a calculation that you already have as part of your project files, right? When you found out what that profit maximizing price and quantity was, I think at that time, you probably also were interested in, okay, what's the actual revenue at this price and quantity? What's the actual cost? And what is going to be our maximal profit? So back a couple of decisions ago, you probably figured out what this total revenue was. And so then you don't have to do any additional legwork if this is how you want to go about the calculation. Right? So one way of getting that consumer surplus is just integrating the demand function from 0 until your equilibrium quantity. And then after that calculation is done, subtract out your total revenue. So that'll get you the area of the purple region, the consumer surplus. The other way to do it, and it's up to you whether this is easier or more challenging, but I think it helps to connect it to some of what you've been learning about the integral in the second half of the course, is anytime we're trying to find the area in between two graphs, we can do that with a single integral by just subtracting the upper function minus the lower function. And the lower function is a constant, it's a horizontal line, and that horizontal line is at my equilibrium price. So in other words, this horizontal line that we see on the graph here has the equation y equals 41.81, right, my equilibrium price. And if I treat that as my lower function, 41.81, and then I just subtract it, so we're doing upper function minus lower function, that is the construction with which we always compute the area in between two graphs on a coordinate system. So in other words, we could subtract this equilibrium price first from the demand function and then integrate. Or, and it's completely equivalent to do it the other way, or we could compute the total revenue separately and then subtract it after we integrate. So it's up to you which one you want to do, whether you want to subtract first and then integrate, or integrate first and then subtract. Either way, you're going to be able to get a computation of that consumer surplus. Supposing that we take this route, where we decide to subtract the equilibrium price from the demand function and then integrate. So how that would look, if I just take the writing off the screen for a second so that we can see the demand function that I actually used to generate this graph, is actually this one. I'm going to write it on the whiteboard for a second. So what I would do then is I would just drop in my d of x function right into this integral. So that'd be minus 0.01 x squared minus 0.1x plus 80. And then I would have minus 41.81, or whatever my equilibrium price was, and in this example that's what it was. And I would integrate that from 0 to 57. And so the magic that happens now is that I'll just simplify this expression inside by subtracting the like terms, 80 minus 41.81, before I do the calculus, which is always a good idea to do your algebra before calculus. Because when it comes time to actually doing the antiderivative, you want that function to be as simple as possible. So I would just do 80 minus 41.81. That's going to give me 38.19. And then now is a good time to ask, now that all the algebra, oops, I screwed up a sign. Let me make that a plus. Now that all the algebra has been done, how do I compute this integral? How do you compute any definite integral? Plug in the numbers for x, the 57 and the 0, but we're missing one step that happens before then that makes it a calculus problem.
Yep.
Yeah, we need, sorry?
I was going to say, don't you have to like raise the power of
Yes, you're talking about taking an antiderivative. Exactly, right. Right. That's what we call the fundamental theorem of calculus. That's how important it is, right? It connects the two halves of calculus, the derivatives that you learn in the first half of the course and the integrals that you learn in the second half of the course. We find out in the fundamental theorem that they are just two sides of the same coin. To compute a definite integral, we'll take the antiderivative, and as you mentioned, that means changing the function so that the exponents, the powers on the variable go up by 1, and then we divide by the coefficients. And then we plug in the 57, we plug in the 0, and then we're home. So antiderivative. So what's going to happen with my x squared? What does it turn into in its antiderivative? X cubed. So the power goes up by 1. What else happens? We divide by the new power. Exactly. So x squared turns into x cubed over 3. And because of the linearity properties of the integral, this coefficient just comes along for the ride, the constant coefficient. So that's what happens to the x squared. The x, what happens with that? Right, because there's a secret exponent of 1 sitting on this x, that when I raise that exponent by 1, it becomes x squared. Divide by 2, and the coefficient comes along for the ride, minus 0.1. And what happens with 38.19? Yes, because secretly, there's an x to the power 0 sitting here. Because x to the power 0 is nothing more than just 1, right? So it's an invisible multiplication. And that shows me that I can just do the same process. Raise the exponent from 0 to 1, divide by the new exponent, which is 1, but I don't have to write division by 1, because that's invisible. And then the coefficient again comes along for the ride, 38.19. And in a definite integral, we don't have to worry about adding an arbitrary plus c constant sitting out here at the end, so we'll just take this antiderivative as it is. Even if we did add a plus c, it wouldn't matter, because the step we're about to do would just cancel it out anyway. So now that we have the antiderivative, now is the time to plug in those values for x. So we'll plug in 57, we'll plug in 0, and then once we plug in those two values, what do we do with them? Subtract them, right. We take the evaluation at the upper limit minus the evaluation at the lower limit. And you'll notice, by the way, for this antiderivative, if I plug in 0 for x, what are we going to get? Yeah, every one of my terms here has a factor of x in it. So when I plug in a 0 for x, everything just wipes out. So our final answer is going to be the result of plugging in 57 into this expression. And so there is then a case to use our calculator. Times 57 cubed over 3 minus 0.1 times 57 squared over 2 plus 38.19 times 57. So we do out all the arithmetic and find out that that number was 1397.07. So the last thing to do then, we took this problem from a business marketing problem into a calculus problem, and then we did the calculus. But before we put this on our boss's desk, we better turn it back into a marketing answer. So what is that 1397.07? It is the consumer surplus, but how much money is it? When we're computing revenue on this chart, what are we measuring? What are the units of that? Thousands of dollars, right. So that's pretty good. That's 1.4 million. Right. So that means that in this particular model, that there's $1.4 million out there in the market in consumer surplus. That if we were to implement whatever price discrimination scheme that we might cook up, right, that we could recapture some of that 1.4 million in additional revenue, on top of the revenue that we would get just from a single pricing structure, which is what you found in the first part of the project.